Maximum area and volume notes, example 2. A cone with its vertex at the origin is inscribed in the paraboloid formed by rotating the parabola x equals 4 minus y squared around the x-axis. Find the maximum volume of the cone. Anytime you see the OID, just means that we've taken a figure like an ellipse, hyperbola, parabola, and we've rotated it around a central axis. In this case, we're rotating it around the x-axis. So first we draw the parabola, and then I'll show you how to draw it as if it was rotated. The parabola is x equals 4 minus y squared, which is going to open in the x direction. Rather than put this in standard form, find the focus and the p, and find p and the focus and all that, it's probably easiest, since all we want to do is make a sketch of it, just to plug in some points. Since the y is the squared value, it actually is easier to plug in values for y and find x. And we know that its vertex is at the origin, so that's one of our points. So I'm just going to make a little t-chart, and I'm going to plug in -2, -1, 0, 1, and 2 for y. So if y is -2, I would have 4 minus a -2 squared, which would be 4 minus 4, so x would be 0. If y is +2, x would also be 0. If y is positive or -1, I would have 4 minus 1, which is 3. And if y is 0, then x would be 4. So let's go ahead and plot some of those points. Oh, it says the cone has its vertex at the origin, not the parabola. I was puzzled looking at that, so I was incorrect in what I said before about the parabola having its vertex at the origin. Let's plot the points. We have the point 4, 0. We have 3 positive 1 and 3 negative 1. So you can see the vertex of this parabola is actually at the point 4, 0. We have 0, 2 and 0, -2. So this is the parabola. Now it says a cone with its vertex at the origin is inscribed in the paraboloid. First of all, let's draw the paraboloid. It's rotating around the x-axis. So I'm going to draw kind of a curve, and then this with the dot shows that's sort of behind. So we're another one sort of like that. So picture this kind of a round looking ellipse or parabola. It's rotating around the x-axis, and it's three-dimensional, kind of sticking out at you. I could draw another one down here kind of to show. So we have more of a dome-shaped figure on its side. Now we're going to draw a cone with its vertex at the origin. So we have a cone here. It's inscribed in the parabola. So I'm actually just going to use this circle I've already made and make that also the cone. So we have a cone. Imagine its edge here. So here's the edge of the cone. The edge of the cone, oops, I sort of moved this a little bit. The edge of the cone here is coinciding with the edge of the paraboloid. So that circle at the top of the cone is also the surface of the paraboloid, and then its vertex is at the origin. We want to find the maximum volume of the cone, the volume of the cone. And I've given you the volume of the cone right here in this. This is the formula for the volume of a cone. Remember that whenever we do one of these types of problems, we have to pick a point in quadrant 1 that is both on the cone and on the ellipse. So I'm going to use this point right here. I'm going to call that x, y. And I want to write the volume of the cone in terms of x and y. So we need to think about what the r and the h stand for. The radius of the the radius of the cone, not coin, is the radius of the circular base of the cone. So it would be this distance from here to here in red that I just drew. The height would be from the tip of the cone to the base of the cone. So this would be the h, and this would be the r. Now, what do h and r correspond to when we think in terms of x and y? Well, h corresponds to x, and r corresponds to y. So we can actually write this then as volume equals 1/3 pi y squared x. Now, just like before, I want to get volumes just in terms of x. So I can think as this point xy moves, slides around in the first quadrant, I'll get all possible shapes of a cone. I could get a really tall, skinny cone. If I move it down more towards the y-axis, I'll get a really short, fat cone. So I could get anything. I could get a cone that looked more like this, or I could get a cone that looked more like this, depending on where that point xy is touching the parabola. I want to find which cone of all those cones has the maximum volume. So what I want to do is substitute something for y squared in terms of x. And I have another equation here. I have an equation of the parabola. Any point that is on that edge of the cone is also on the edge of the parabola. So I can substitute into the equation, solve this equation for y, and I have x minus 4 is equal to negative y squared, or I can say negative y plus 4 is equal to positive, negative x plus 4 is equal to positive y squared. So I can substitute negative x plus 4 in for y squared. Or maybe I'll just write it as 4 minus x. That'd be a little easier. So I have volume is equal to 1/3 pi times 4 minus x. Notice I'm not squaring it because it's 4 minus x equals y squared times x. And if I were to simplify this a little bit more, I have 1/3 pi times the quantity 4x minus x squared. And I could distribute again if I want to, but that's sufficient for our purposes. So now I want to find the maximum volume. So I want to make a graph where x is on the x-axis and volume is on the y-axis. And that's going to go up and come down probably in some way. And I want to find that maximum volume, and where does it occur? What value of x does that occur? So I'm going to put that on my calculator and do the maximum. So once again, here's the equation. I need to make a graph page. So insert a graph page. Type in the equation, which is 1 divided by 3 times pi times, in parentheses, 4x minus x squared. Where'd my x go? Minus x squared. Okay, and I'm going to graph that. Now, what values before I graph it, let's think of some window settings. Well, I'll go ahead and graph first, and then we can do some window settings. So if I enter, I get this graph here. Now, what portion of the graph am I interested in? If we go back and look at the notes here, I'm specifically interested in values of x that are going from 0 to 4, because those are the only possible values I can have. And I'm only interested in positive values for y because obviously I don't have negative volume, because y represents volume, or f of x represents volume on the calculator. So going back to the calculator, let's just change our window settings here. Looks like I'm really okay here. I'll just maybe make this 6. Tab over here. I only need 4. Why don't I make it, yeah, I'll just make it 4. That's fine. And then I don't really need any negative values for y, so I'm just going to make that 0. And I don't really need any negative values for x because I don't need x, that's a distance as well. So that gives me a better view of what I'm trying to find. And obviously here's our maximum is going to be right up here. So if we look at going to the menu again and analyzing the graph and going to maximum, I did figure out what you need to do. You need to use your little scroll, use your touchpad, scroll that line over until it's to the left of the point of intersection, or the maximum point, then click. And when you click, then you're going to drag that over until it reaches the maximum, and then you can click again. And there's my maximum point. It'll it'll give you the maximum point. So you click to the left, drag it to the right, click again once you see the maximum highlighted. So we have the point 24.19. So think about what that means. And I'm going to take this and move this into my document so we can look at it in here. So you're going to want to make this sketch on your paper. I want you to make the sketch. I want you to write down the equation you use and make the sketch and show the point of intersection. And your conclusion then is the maximum volume of the cone is 4.19 units cubed, because this is a volume. Now, where does that maximum occur? When the cone has a radius, because x represents the height, has a height of 2 units. So what is the radius of the cone, and how can you figure it out? Well, if we know the volume is 1/3 pi r squared h, and I know the height is 2, and I know the volume is 4.19, so the volume 4.19 is 1/3 pi r squared times 2, and solve it for r squared. So multiply both sides by 3 and divide both sides by 2 and pi. So 3 times 4.19 divided by 2 pi is equal to r squared, and take the square root of that whole thing and we'll get r. So when we calculate that, go to a calculator page. So it's the square root of 3 times 4.19, I probably should have done, divided by, in parentheses, 2 times pi. And that equals 1.414. So let me go ahead and put that on there. And a radius of 1.4 units. So there's our maximum volume. And I forgot to do that last step on the previous problem. So I'm going to take us back to the previous problem and find the other dimension of the rectangle. So we have our cone and both of its dimensions. Now if we go back to our rectangle, we said that the maximum area was 30 units squared when x was 3.54, so that would be one of the dimensions. That's actually only half of a dimension. So what are the dimensions of this rectangle? Well, since the area is 4xy, so the area is equal to 4xy, or 2x times 2y. We know that the dimensions are going to be 2 times 3.54. Let me get that quickly. 2 times 2.54, 5.08. And then the other, if we have 30, is equal to 4 times 3.54 times y. Or actually, it'd probably make more sense to just say 30 is equal to 5.08 times the width, so height times width. So 30 divided by 5.08 would give me the other dimension. And the other dimension would be 5.91. So the dimensions are 5.08 units by 5.91 units. And those are the dimensions of the rectangle that have the largest area. This concludes the notes on maximum area and volume.